I got the green light. So since I'm, I think, new to you, because I don't appear that much in the academic community, I thought to introduce myself a bit on what I've been doing. So I started in electrical engineering. Not sure if it's similar to your background, but if you look at electrical engineering, it's a nice mixture between physics, software, and hardware, and you all get that collected in this one course on electrical engineering, or one, well, what is it actually? It's not a course, it's a study, it's a 5 years of electrical engineering. I finished in systems and control, kind of like the counterpart of DCSC over here in Delft. And after that I did a PhD at the institute that I already worked. So I started working at TNO. I started doing a PhD in Kalman filtering, all sort of exotic variations of that. And after that I always was within the university for 1 day a week, and then at TNO for 4 days a week, so from my PhD on. And I went to Karlsruhe, Stockholm for a while. And now I'm here in the group of cognitive robotics for that 1 day a week. Now at TNO I started as a scientist, still am a scientist over there. Just as the age goes, you also increase the people that you work with, or the people that you guide and supervise. And I started in the field of image processing, just around here at the corner, computer vision, detecting stuff. I think it was bubbles back then, because there was some glass which is boiling, and then you should know whether it boils or not and how much it is boiling, so you should count the amount of bubbles, and we did that with imaging. After that I continued to sensor networks in relation to my PhD, so Kalman filtering in sensor networks, and now I am in autonomous robotics, multi-agent systems. You see a bit the stuff that I work with on the left. So we started off with ROS Gazebo, I think 4 or 5 years ago. ROS 1, we are now at ROS 2, but back then it was still ROS 1. My background, or the domain that I work with is very different. I started off with traffic, vehicles, climate control of greenhouses, not the greenhouse effect, but greenhouses that we have here in the Netherlands. And for some years now, the facility that I work with has a relation to the Dutch military. And for that reason I also have these kind of projects. So we start off in, for example, guarding, surveying some kind of military asset that should be kept secure. Well, we do that in Gazebo, we also do it in the real world. I think up until a couple of years ago we worked with these more toyish systems. So we bought a drone and a car, and instead of making them remote control, you can buy hardware to make them, to give them a waypoint, and then we'll go to that waypoint. And from that point on you can start increasing their intelligence. I also work with these kind of underwater systems. I understand that you already covered them quite heavily. We have 3 of them. What we do is we use them to scan the seabed in order to look for man-made objects, which can be mines, but also bombs for the Second World War, because during that time of war, the Germans flew to London, dropped bombs, head back, but they didn't have enough fuel to really get back if not all bombs were dropped. So in that case, they dropped their bombs in the North Sea, and there's a tremendous, it's estimated about 40,000 Second World War bombs in the North Sea, so in between the Netherlands, Belgium and England. And the Dutch and the Belgian has got the NATO duty to get rid of this and to make sea lanes for trade, for ship trading. And that's why we use those systems also for. Scanning the seabed is an enormous task. I think so. 3/4 of the world is covered by sea, and we did not cover it as accurately as with our GPS systems in space. These systems might help us with that. So we run tests with them. You see that seals are very attractive to these kind of systems. So they're very curious animals. So whenever you do these kind of experiments, and seals are near you, you'll get them on your camera image as well. There's also one that was in, I think in Shark Week, they used a REMARO, and they said to test the strength of it, but they put a tracker on the shark, and then this REMARO vehicle was there to just walk or swim or sail with this shark at distance, of course. The shark got annoyed by it because it, of course, has this electromagnetic sensitivity that this AUV is spreading all the time, and this shark is using that to get its prey. And it got so annoyed by it that it attacked the REMARO, and it really grasped it, but it didn't tear it apart. So REMARO said, look at how strong our system is, it can even survive a shark attack. Other than that, so I also like to do these kind of, so if you are at TNO, at university you always ask, how do you, what's your application, what's your domain, what do you use it for? And I actually like the stuff that I don't have a domain or any application. So I started off with some students, and they got all these questions, what's the use of it? Well, just for having fun. So in this case, we had this small robotic car, and we put it underneath a bigger car, and I asked the students to make some kind of a controller to keep this car under the bigger one. So you'll see it over here, and it's the car is now just in a straight line, and the RC, the small RC, is keeping its position within the two front wheels. And we also tested it, of course, with angles and so on. It could go up to 50 kilometers an hour, and that was more or less the max, which was great fun. It was my introduction to ROS and to Python, because before that I always worked in MATLAB. And we did the same thing, but then with flying drones. Now this is all, it's a military project, so you'll see that it's got this bombastic music going on that you might have heard while you were drinking coffee. The idea is that there are 3 drones to scan an area. 2 drones are sent out to do the typical LOMO pattern. If they see a QR marker, then a notification is sent to the 3rd drone to make a close-up identification, and you'll see that in the video. Oh. Oh, it's still a bit glitching. I'm not sure what happened. We are over here, and these are the duct tape drones we were using. That's the marker that we needed to detect. So all computing was done on the drone. The entire demo we were sitting with our hands on our back, not doing anything, but just sending the first command, search the marker. So the 2 drones, they got up in the air, and each of them got an area doing their LOMO pattern. They've been using the Steve Blue. Yes, yeah, we did. Yeah, so we got some kind of bounce. Yeah, and we didn't want to spend too much time on the imaging, on the camera vision, so for that reason we used the it was about that we were able to send tasks automatically. In the meantime, it found, one of the drones found the QR marker, and the 3rd drone is now making a close-up of the marker, and they all go back to their home position once they're done with their task, and all was well. And for the entire, I think, 10 minutes or so, we were a bit with our hands on our back. So the idea of making a system autonomous is not to have any kind of human intervention, as little as possible. So during any kind of demo or experiment, I want to be as fast as possible to be able to give the demo. So I don't want to spend 2 days before on that same spot to make all some kind of code adjustments and then run the demo. I need to go there, and in 1 hour I need to be able to give that demo without any intervention and go back. That's more or less the philosophy that I try to achieve. Now, looking back a bit in the setup of these kind of systems, we started off with this classical scheme, I would say, if you forget about the knowledge on the top. Then you get the typical OODA loop, so the observe, orient, decide, act. So you do some filtering, you extract information from your sensor data about objects, where they are located, where you are located. You put that in some kind of a state information database, and you use that for planning and scheduling. You can use MPC for planning and scheduling. You can use PDDL, task networks. There are different methods that you can use for that. And eventually you go to some kind of a low-level controller that really controls your platform. You can have all kind of settings of these functions. So gains for your PID controller can be set and tuned according to the situation. Models that you're using in CAML filtering, depending on what you're tracking, you can set different models. These kind of things can all be set, and you should set them, because if you hand code them and you go to a different application or a different domain, then you need to redo them all again and again and again. And that kind of is annoying, because you should search for those parameters all the time. So what we try to do is we try to give the robot some sense of knowledge about the world, and given the situation it is in, it should be able to set those settings. So it's kind of like the first step into self-adaptation. Which is knowledge exploitation, so capturing the models from our knowledge base. You can also have some knowledge extraction, so from your information learn new knowledge, or instantiate knowledge. So if I know there's a human and I actually see a human, then I instantiate the concept human as information. And this is basically our setup for the last few years. There is some limitations to it, because it has a strict decomposition, so you either are in this or in this or in this or in this, which is sometimes annoying. And also typically the architecture behind is the ROS2 setup is your public subscribe mechanism. So you publish on topics, and other components subscribe on topics, and that's not very flexible. We'll show you in a bit. Yes?
I just looked up the OODA loop, and their definition is observe, orient, decide, act, object.
Oh, sorry, that's a glitch. It is observe indeed. Okay. Yeah. Because also, you'll see it in a bit, we have this spot robot, and it's searching for people, for victims in a house, and it should be able to identify these people. And searching, you can search in two ways. You can do it typically with a camera and visuals, and you're only able to do that if there's no smoke, light conditions are well enough, and so on. Then you're able to scan a room and search for humans. If there are smoky conditions, and we'll test it in smoky conditions, or dark conditions, then a camera is a bad selection. You can do it with audio, so you can let the robot shout, "Is there anybody here?" And if the person is still conscious, it can shout back, "Yes, I'm here." So there are two ways that you can search for people. And depending on the environmental conditions, one is better than the other. And how could you select the proper one, the proper behavior? That's up for a planner to decide, but you can give it input as to what performance would you expect from those two behaviors. So each one of us is a behavior. Now here you see the different setups of those behaviors. So for the one, you need of course a camera and some object detection module and a path planner and some localization and autopilot, but that's typical. And for the audio one, you need a microphone with some speech recognition, natural language processing, and you need some kind of a waypoint and a dialogue planner, because you are having some kind of a dialogue with a human who hopefully is conscious. So these have two different setups. If I would use the publish subscribe mechanism, then all these modules should be turned on all the time, spitting out their information, which is basically occupying the network quite heavily, especially if you have bigger cameras, and accurate microphone data, because it samples very fast. So we came up with if you look into ROS, you also can have services and actions. And with a service, you only acquire a particular piece of information or a particular processing capacity in case another one really needs it, if it needs that service. So we went more towards the service-oriented setup. And then the OODA loop is not that useful anymore. And I have some examples on that. So we start with, we have some server and some drivers. So we need drivers to collect our hardware into our system. A camera driver, a microphone driver, a platform driver, whatever. And we have some server on top of that to make the hardware a bit of agnostic. I think agnostic is the right English term, yes. To the rest of the system. So that can just send a waypoint, and that the driver, being it for a drone or for a quadruped robot, will just execute that. And we schedule everything with a behavior executor, which is basically a behavior tree. And this behavior tree is, if you look into how behavior tree works, you have this basically the sequence, and then you first have a check: is my battery okay? If my battery is not okay, go charge. If my battery is okay, I go to the next sequence, and the next sequence is move to an object, then close your gripper, and then move home. So it's basically you pick up something and you collect it. That's what this behavior tree is about. And each of those low-level behaviors, the primitive ones, are actually services that we call in this right side. I think indeed, yeah. Oh, you can click it quite nicely. Okay, good, we continue. So this behavior executor has different behavior agents, and each agent is responsible for a behavior, so the visual search or the audio search. And it's a set of predefined actions or services, so you can call those, we now implement them as services, you can also implement them as actions. Each action is either to acquire a piece of information, or to manipulate the environment, or to have some other primitive action that you want to have your system to be able to execute that. So acquiring information is an explicit action. We don't wander around here gathering all sorts of information and running a detector all the time, which is checking objects in this room. It's an explicit service that you ask, get a camera image and please analyze that image for me. And I'll have some examples for that later on. So if you look at our robotic system, the robot itself is already quite complex, but we have some kind of a navigation driver able by which we can give commands to this robot. We have an environmental driver containing a light switch, a light sensor, a gas level sensor, and a dB meter, so decibels. We could do the same thing here on our microphone array, but we use the microphone array to record audio for speech recognition and these kind of things. We also have a speaker by which we can say what the robot is doing, which is extremely important because otherwise you're looking at the robot and you think, what is it now doing? And if you use a speaker, if it basically says what it's going to do, it's very for debugging purposes very handy. We have two cameras. Well, one camera actually. We have multiple ones. We have the double pan-tilt zoom, but we also have just an RGBD, the Azure Connect camera. And we have other kind of hardware, for example, the TPU for image processing purposes, for trained neural nets and object detections. And these are all, queried, asked, serviced by the behavior executor. And by that we can have a list of behaviors. That's the nice thing. So we have some typical services that each of those have available. And then if, for example, we want to search in a fast way, we want to search a room in a fast way, which basically means we have entered the room, we are in the doorway, and it's looking in multiple directions in order to see whether a human is there or not. Then this is actually the schedule of our behavior tree. So we orient ourselves to the center of the room, and then for a number of angles, we take the image, We analyze the image on whether there's a human in, yes or no, and if the result is true, then we write the human to the knowledge base and continue to the next angle and so on. And then actually it looks like, well, you also see the exit via door case. Not sure actually, can you see it in the back? Yeah?
I am in room, hall. I will exit this room via door, living door.
There's still some audio issues here, but it says that it's going to exit
I successfully
via the
finished
door.
operative action exit via door. I'm going to quickly look for victims in room living.
So it says it's now going to conduct a fast search, and then it will have these different angles. And then it's actually done.
I successfully finished operative action search in room.
And this is also an important one, the fact that it knows that it successfully finished it, yes or no, because normally you wait for 20 seconds or 30 seconds or a minute or whatever you're waiting for, but if it can deliberately analyze whether it is done with its action, so whether it has completed its entire behavior tree, it should say that so that you can continue. Otherwise it failed. Now with this thing we can have multiple, with this setup we can have multiple behaviors. So for example, if you would do an audio search, it's also basically standing in a doorway, and then you call services like speak, is there anybody here? You listen for 3 seconds, you analyze the reply on a particular language, and if somebody said in any language I'm here or whatever, then you say there is a human, and you write it back to the knowledge base. So you see that this is basically the same service as before. And then it looks like this, but it's only audio, so I'm not sure whether you
I'm
will.
going to listen for victims in room living. Is there anybody here? Is there anybody here?
Yes, Spot, I'm here.
Successfully finished operative action search in room.
So now it knows that, so it tries a number of times, and now it knows that it's done because somebody replied, and it knows I'm done, I can do, my next action may be planned. And we have all sorts of behaviors now. We have a identification, so we approach and we identify a person, we exit a room via a door, we have the more thorough search, either with the light or without the light. And all of these services that we have available, by scheduling in the right order, we can have a number of behaviors. And the nice thing about these services is that they only become active when you ask them. So you'll save computing time, you'll save other communication resources, up until you need that behavior, and up until you need that component and the resource that component is giving you. So in that respect, it's much nicer than the classical OODA loop setup, which is more restricted. And this is more or less the picture that we have right now. So we have all our behavior agents in our behavior executor, which is basically some set of internal components still. Those are the drivers and the servers that you found over here. And then based on their output, either I analyze my system, my behavior, whether it's properly working, yes or no, or I write back stuff that I need for the environment. So if I find a human, then I'll put it in the external situation. And that's going to be sent to my task planner, and my task planner is basically sending which behavior to execute next and next and next. And by that, I will be able to search the entire house, is search for humans, and if there's a human, to identify them more or less in 20 minutes.
Aren't the roles actually collaborative?
Have you specified some behaviors that are more like a collaborative or through communication? For example, the swarm scenario that you introduced earlier, is the area are all robots operating in the same area, or there is some kind of separation between the different areas?
Yeah, in this case we don't use it for this robot. What we do, for example, is that we have services available to acquire information from the knowledge base. So everything that's not known to the system, it can query the knowledge base. You can have a similar one to query another teammate. That's one thing that we are thinking about. What we do develop now is to give tasks to either our robot or to another robot. So how can I, what is it called? It's not called task decomposition, it's called task delegation. So how do I define a task, and what do I need, what does the other need in order to execute the task?
At the moment it's more central, as I understand, right?
Every robot has a central knowledge base, but the other robot also has its own knowledge base. And by this, but we are now defining basically the message structure that we need in order to give tasks to other robots. That's what we are defining right now, and that can then be a service that might be scheduled by the executor. Yeah.
What is the self-X box there?
Yeah, well, that's the rest of my presentation, which I will not cover in 15 minutes, but that's okay. I'll give a bit of a flavor for this. So we want to create autonomous robots. That's our purpose. And autonomy means that it's able to deal with stuff by itself, not by a human operator. So if we can limit the amount of interventions from a human operator, if we can decrease it, then we're happy. Then we say our system is more autonomous. Of course, we cannot imagine that if we are in a very complex environment that the robot does not need any intervention. So the more complex the environment, the more interventions you should expect. But overall, we want to decrease that line. And the thing that basically self-X is doing is that it's basically asking itself this question: am I able to do this task? Which basically means, can I do behavior I? And then I is either agent 1, 2, or 3. Given the current circumstances, given the current situation, would I be able to execute this task? And for that we need, and that's the symbolic part that Carlos was talking about, we need some kind of a knowledge representation about our components and how these components are clicking together to form the entire behavior. And that's the modeling part that we are using. Some kind of available solutions that are out there. So there's a lot if you look into system modeling, so SysML and these kind of solutions. The functional decompositions, you saw the ODA loop. You also have MAPE-K or 4D RCS as approaches by organizing, setting up your system. And there's also solutions for self-adaptation, which go more on the online part. So Tomas's and meta control of Carlos is one of them. You also have robust sense in intelligent vehicles. There are some flavors. Typically, they either go for a data-driven or a knowledge-driven approach. Sometimes you'll have them as a combination of the two, but very rarely they take the environment into account. So it's only basically by internal readings and not understanding in this type of environment I should do, this component works well or not. So that's our edge, so to say. I'm not going to dive into the hypergraphs. How many of you do know knowledge representations and ontologies? Okay, so. So if you want to represent knowledge, you should question yourself, how do I represent knowledge? How does a system understand something? And knowledge representation is the key to that. You can have hierarchies, taxonomies, in order to decompose objects in the world. That's one type of knowledge representation. I always tend to go to ontologies, which is a more richer way to represent knowledge. It depends a bit on your problem and how complex your problem is, which type of representation is most suitable. If you look at ontologies, you can represent them as a graph, and your typical graph has one node and one type of edge. If you go to hypergraphs, you can have more types of nodes, which is in this case here. So I have here 3 types of nodes: the square, the diamond, and the ellipsoidal one. And I have 2 types of edges. I have a has edge. So in this case, node E1 has the attribute V4, whatever that may be, and I have that an entity, so a real thing in the outside world, is having a relation with another entity in that world. That's basically what it's represented. And that's represented by roles. So, for example, I am a human, I am an adult, that's my entity, and I have a relation with another human entity, for example, Carlos, as being his colleague. That might be a relation. But I also have, and that's then the same entity, I also have another role, more of a family role with my wife and my 2 boys. But the entity is still the same, but the role that I play within such a relation may differ. And then, of course, how do we do that to model a system? And we have basically, we decompose it into 2 parts. We start by modeling individual components. And once we're happy with how we modeled individual components, we can see how they model an entire behavior. And this is our design for a single component, the most highest level of design pattern that you might have. So I have a component, anything, in my system, which is a petitioner, so it requires stuff. And it requires, well, once everything that it requires is satisfied, it can create some kind of a product. And the creation has some properties. So data is a creation, for example. Energy is a creation. Noise is a creation. What it requires other creations. So data often requires data, it requires computing power, it requires some other stuff. And that should be, that creation should feature particular properties. It not necessarily has to have those properties, because you might have some kind of a selection. I need an accuracy in between 0.10 and 0.2, for example. So that's how we circumvent the has property. I'll give some input for that later on, or some examples. But this is our main model. And then we can decompose what we know of a system. So we have several components. We have sensors, actuators, we have some kind of a functional component, and we have appliances. And we have different types of creations. We have data, we have resources, we have physical phenomena. Those are all creations. A data is, for example, signal, information, and knowledge, whereas a resource is electrical power, computing, and physical phenomena are sound, light, and speed. There's always discussion and debate on whether those terms are the right terms, which is, of course, perfectly fine. But the hierarchy and the structure is what matters most now. And if you combine, I also think I have, so we also have properties, so we should characterize our data, our noise levels, and these kind of things. So we should have properties. So, for example, a rate by which data is being sent, quality, location, where might I find my data, so the virtual location, but physical phenomena have a physical location. Throughput capacity, for example, if you care about your energy of your system. The format, so what is the format of my message type or of the resource that I get, how is it computed, the quantity itself, and some range. And if you look into system engineering, there are different requirements. So you will have functional requirements of your system, you would have non-functional requirements of your system, of components, sorry. And you also have environmental requirements. As I just mentioned, a camera would only work under particular light conditions. And if you now bring those all together, and I only take the example of a functional component, then this is how I could represent one component. I have my functional component. It is producing data as output. That data is being characterized by some kind of an update time, some kind of a quality, a format, and a location, a virtual location in this case. And I have my 3 sets of requirements. And if those are all required, only then my data is created in the proper way. And my functional requirement has other data, requires some data input. My non-functional requirements require some kind of a resource, and my environmental requirements require some kind of a physical phenomena. And by that, I've characterized one component, in this case a functional one. And I think I even have an example, and then I'll stop. So if you would look, for example, for a camera, then a camera, I have a component, an RGB camera. It has, what is this? This is the data it is creating. It's data called an RGB image with particular properties. So for example, you can find it on the ROS topic, image raw, for example. That's the location where you can find it. It has a particular contrast and so on. It requires also electrical power, so I need electrical power featuring, well, a minimum of 5 watts up until infinity and a voltage of exactly 5 volts. And it also requires some light intensity with a particular spectrum, so the visible spectrum and light intensity, so a particular lumen. And then you can collect all this together.